Well, mm, week 12 discussion session. Formally, this is the last week of the official discussions that we had. But we are in talks of having one more additional week. Uh, we generally call it as an extra session, which would be so it is not confirmed yet. As and when the extra session will be confirmed, it will be posted in the website, and also you'll be notified through emails from the NPTEL administrators. But yes, so mostly the extra session will be held in the next Tuesday, that is the coming Tuesday, and it will be week 13. But formally, this is the last session of this course. I mean, last means the last live session of this course, and we'll begin today's session by, as you know, we'll be briefly going through what we saw in the last week. And if you remember, basically we looked into something which is known as radiation exchange between surfaces. And first and foremost, we begin by understanding something which is known as the view factor. And what we did is by formally, considering differential areas having, and differential area of dAi and dAj, we established the expression of a generic view vector Fij, which is nothing but the fraction of, radiation leaving surface I that is being intercepted by surface J as an integral over this integrand. And if you closely have a look at this integrand is just a function of orientation of those areas only. Okay. For instance, this cos theta I times dAi is nothing but the area which is normal. So it's basically the normal area in the direction to which you are basically looking at. Okay. And so is this area cos theta j times dAj. Okay. And of course, this distance r was the distance of separation between the centers of those differential areas that we are looking into the picture. Okay, so this view factor, which we call it as Fij, is nothing but the integral of this integrand, which is cos theta I times cos theta j divided by pi r square. And this integral is of course divided by 1 upon ai, that is the area of the ith surface that we are basically interested into. So the bottom line was that this view vector is actually a function of its orientation. The generic expression of view vector has, it has nothing to do with the temperatures or the emissivities or, any surface properties. So this brings into an important conclusion that, you know, the view factors are basically determined by orientations. That's it. It has nothing to do with, as I said, it has nothing to do with, surface properties like emissivity and all those emissivities and temperatures and things like that. Okay, because it just goes from the basic definition of view factor, that it just states that what is the fraction of radiation that leaves a surface I that is being intercepted by surface J. Okay, so we had a close look at this expression of view factor, which is Fij, and similarly we argued that thus a similar expression for Fji can also be determined if we just replace that Ai with Aj now. Okay, and then I said that since this integrand is basically the same, which is nothing but this product of cos theta I times cos theta j divided by the pi times the square of the central distance. Since this integrand is the same, I can easily say that Fij is equal to Fji, and we saw this famous relation as the view factor reciprocity relation. And we argued that for any generic surface, this relation holds true. Okay. And thereafter, we saw one more relation associated with view vectors, and that is known as the summation relation, which states that for any ith surface, the sum of all the view vectors associated with all the all the other surfaces, that should always go. So if you add all those view vectors, it should always go on, and it should be equal to unity. Okay, that is typically because these are fractions of energy. So if you add the total fractions, you should always get the total amount of energy. Okay, and that's the logic behind this summation rule for view vectors. And then we looked into certain numericals. For instance, we just solved the numericals, which asks that if there is an enclosure and if there are n surfaces in an enclosure, how many view factors are needed to be, a priori known or determined directly. Okay, and then we argued the fact that if there are n surfaces, the total number of view factors would be n square, out of which n number of view factors can be determined from the summation rule, and the rest n into n minus 1 by 2 view factors can be obtained from the reciprocity relation between the surfaces. So in a way, if you have n surfaces, then the total number of view factors would be n square. out of which n would be determined from the summation rule and n into n minus 1 would be determined from the reciprocity relation, meaning that if you subtract this n and n minus 1 from the total view factors, this many number of view factors, needed to be known directly or, a priori. Now, we saw by a couple of examples in the last class that sometimes the symmetry of the problem assists us in this regard. Okay. Out of these directly, obtainable view factors, some of the view factors can be easily argued upon. Okay, just by looking into the physical picture or the symmetry, if there are any symmetries that arises in our problem. Okay, so that's the idea behind obtaining view factors, which are to be, determined directly, or else you cannot basically determine these by using either the summation rule or the reciprocity relation. We then solved a numerical, okay, involving the general integral form of the view factors, which was basically required to find this Fij. And this numerical was pretty straightforward. We just have to use this form of Fij that we just now saw, and then use the fact that these surfaces are parallel. The only complexity of this problem is that this surface J, instead of it being now a differential area, it is now a disk, okay, having a diameter d. So what we need to do is we need to choose a small strip. So what we did is we choose a small strip in this disk, find out the differential view factor associated with this small disk, and then integrate it from radius of 0 to d by 2. And that is what basically we did. Okay. And keeping in mind that what will be the radius, the infinitesimally small daj, which is nothing but 2 pi r dr. We evaluated this Fij and then integrated, as I said, we integrated it from 0 to d by 2 to obtain the expression for Fij, which, came out to be d square by d square plus 4 times L square. And there is just a 2 that I missed here. It should be a 2 here. I mean, it should be square of this. And yeah, the rest, this is something that we did in order to evaluate this Fij. Thereafter, what we said is we also looked into some simple problems where we could easily evaluate view factor just by using the reciprocity relation and the summation rule without having to use the integral form of view factor that we did in the previous sum. Okay. So we argued that. So basically what this sum asked us is to evaluate this F12 and F21 for different three surfaces that you can see in your screen, out of which we evaluated the view factors for F12 and F21, where we just use the summation rule and the reciprocity relation and the fact that things may be symmetric, and or given some clues that we get from the physical picture that we are given in this problem, we tend to evaluate the view factors. Okay. In this context, what I said is I asked you to solve this problem 3, and I asked you to basically solve it at home. And today we will begin by giving you an idea of how to solve this problem 3, and then we will move into the discussions of today's session. Okay. So if you remember, in problem 3, it's a cylinder, okay, which essentially have three surfaces: one, the upper surface; two, the lower surface; and of course the curved surface that the cylinder has. These surfaces are named as A1, A2, A3, bearing areas, of course, A1, A2, A3, and the surfaces are named as 1, 2, and 3. But so the question states that the diameter of the cylinder is equal to its height, which means my L, or you can say H, is basically equals to D. Here it says that L is equal to D, but this is given in the problem. Having said that, they are asking us to evaluate what is F12, that is the fraction of energy that is leaving surface 1 that falls on this curved surface, and F21, that is the other way around, that is the fraction of energy that is leaving this curved surface that falls back onto this this flat area of the cylinder, cross-sectional area of the cylinder to be precise. Okay, and we will start this. So I gave you a hint. If you remember, in the last class I asked you to look into the view factors that can be calculated for coaxial disks that are separated by distance. Okay, and this is a hint to actually solve the view factors that we are asked for in this problem. Okay, so we will see how it can be done. So okay, so for the third problem, so I'll just I hope you have done this problem at your end. This is just to provide clarity, and you can just cross check your results that you are correct or not in this regard. So what we had is we had just a cylinder having some having a surface in this way, and although it doesn't look like this, maybe I'll draw it in a better way. This is one surface of the cylinder, this is the other. surface. So what they say is this surface was given to be equal to 1. The name of the surface was of course 1. The curved surface was 2, and of course this was 3. Okay, and it has been given that your d, that is basically the diameter of this cylinder, which was d, and the length, which was l, is also equal to d. That is being given in your question. In this regard, they just ask us to find F12 and F21. Okay, so let's first start. So this is something that we need to find out in this exercise. So let's just start by trying to solve this F12, where this F12 is nothing but the fraction of radiation that is leaving surface 1 that is intercepted by the second surface. Okay, all right. So what we will first do is let's first apply. So as a first step, let's just go ahead and apply the summation rule in this context. So if I apply, applying the view factor summation rule, what we get is, if the summation rule is, applied for surface 1. So applying the view factor summation rule for surface 1, what we get is F11 plus F12 plus F13 is basically equal to 1. Out of which, again, from the physical nature of the problem, it is pretty evident that if there are radiation that is leaving surface 1, it cannot just go back and hit surface 1 again. Meaning that this F11, has to be equal to 0. And this is from the nature of the problem, nature of the physical nature of the problem that has been given to us. And this is obvious because this F11 is a flat surface, which means if there are radiation that is leaving surface 1, it cannot just go back and fall into surface 1. Okay, so this F11 is 0, which means, this F12 plus F13 is basically equals to 1. But here is a problem that we don't know what is this. So we neither know this F13, that is the fraction of radiation that is leaving surface 1 that hits surface 3, or neither we know this F12, that is the fraction of radiation that is leaving, this surface is being hit by this surface. So what we will do is we will first try to figure out what will be this F13, okay, because of the fact that these two surfaces are kind of like coaxial disk, and we have the generic expression for view factors for two coaxial disks that are separated by a particular distance. So what we will do is we'll first try to figure out this F13, and then using this summation rule we'll then figure out F12. And if these things are known, F21 can be easily obtained from the view factor reciprocity relation. Okay, so we'll do that. So first what we'll do is we'll find out, try to find out F13. So for finding out F13, you need to look back into, what you need to do is you need to go into table 13.2 in the book of Impropera, the principle of heat and mass transfer by Frank to Impropera. If you just go into any edition, the table should be 13.2 of the book of Impropera. So if you look into this table, they have said that for two, for two discs, let's say I have two discs. So what this table have stated as that if I have two discs, okay, the diameter of these discs could be arbitrary. For instance, if I have these two discs, okay, bearing some radiuses R1 and some radiuses R2, and they have a separation distance of, let's say, some L or some X. So if this is the scenario, okay, if this is the scenario, what you need to do is the view factor F. So if this disk is 1, let's say if this disk is 3, the view factor F13 can be directly obtained by using the following relation. So F13 is basically equal to 1 upon 2 S minus, S square minus 4 R3 square by R1 square. Okay, I'll name this as 3 because this being named as 3, this is just 3. It is just 4 R3 square by R1 square, and there is a half here. Okay, and that's it. where this S, okay, where this S is equal to a number which is 1 plus, 1 plus 1 plus R1 square by R3 square, where R1 is nothing but the ratio of the radius of the first disc to the separation distance, and R3 is nothing but the ratio of the radius of the second disc to the separation distance. So in a way, if you know the radius of these two discs and you know the separation distance, you directly know F13 just by using this relation. Now, for our case, luckily, what we have is, so this is a generic relation. Remember, this is just a generic relation, okay? But for our case, so for our case, luckily, what we have is, we have R1 equal to R3 because the radius of, because the radius of these two surfaces are exactly the same. So we can just say R1 is basically equal to R3. And of course, this can be written as d by 2. And this means that my S, so the number S that I wrote here becomes 1 plus, R1 square. But we know that my capital R1 would now be equal to R1 by L, and I know that my R1 is nothing but d by 2 and my L is nothing but d, which means that my capital R1 is just equal to half. Okay, that's obvious, right? Which means that my S is now 1 plus R1 square, so R1 square would be just 1 by 2 square divided by R3, and also R3 would just be equal to R1. Again, the radius of these two surfaces are exactly the same. So this would just be, so the S would just be equal to 1 plus, this term, 1 plus half square divided by R3 square, and R3 is also equal to 1 by 4. Okay, which means my S simply, turned out to be 1 plus, this is 1 plus 1 by 4 divided by 1 by 4. And if you just calculate, this becomes what? This becomes equal to 5 by 4 by 1 by 4, which means my S simply comes out to be equal to 6. Okay. And then if I substitute this value of S, if I just substitute the value of X into this expression, okay, I can just simply write this, so if you just substitute the value of S here, you will simply get your F13. You just do it at your end. You should get your F13. So that should be equal to 0.172. That's it. Okay. You just do it at your end. You should get your S to be equal to 0.17. Just you need to substitute the value of S into this expression, where you already know that this R3 and R1, these are just equal. So this should just cancel. This would be just 6 minus, this would be 36 minus 4, and then there is raised to the power half. You just need to do this, and then there is divide by 2 to basically calculate this F13. If you do that, you should get F13 to be around 0.172. I hope you guys have got this answer as well. So this means you now know that your F13 from this calculation. Okay. So now if you know F13, what you can do is you can use this equation to basically calculate F12. Okay. So that is basically the summation rate. So from equation 1, F12 plus F13 is equal to 0.172, and this is equal to 1, which means your F12 is just equal to 1 minus of 0.172. And if you do this, what you should get is, you should get your F12 to be around, you should get from the answer that I have, you should get your F12 to be around 0.828. That's it. That is one of the first few vectors that the question wants you to find out. Okay. Now, we need to find out one more view factor, that is F21. For that, what we will do is we will use the view factor reciprocity relation. So what now we will do is using view factor reciprocity relation, I can, simply write. So what I can write? I can write that A1 F12 is equal to A2 F21. Okay. And this means what? This means that my F21 is nothing but A1 by A2 into F12, where this A1, so what are these areas? So these areas are, so A1 is basically this area, which is equal to pi by 4 d square, and A2 is basically equal to this area, that is the curved surface area, which is pi dl. And L, you know, your L is basically equal to d. So that's simple. It's just the cross-sectional area and the curved surface area of a cylinder. That's all you need to write. So it is just pi by 4 d squared. Okay, that's A1, and A2 is pi dl. And L is of course equal to d, so it just becomes pi d squared. Okay, and this times your F12, and your F12 is equal to, that is equal to what? It is equal to 0.828, which means, you know, this pi and d square will cancel out, which means what? Which means that your F21 is basically equal to, you know, F12 by 4, and that is nothing but 0.828 by 4, which, you know, straightforwardly comes out to be around 0.207. That's it. That should be your F21. That is the other vector vector. So I hope you guys have got these two answers. If you have not done it, please do it at your end. It's a good problem. You know, we utilize the fact that what would be the view factor if there are two, you know, coaxial disks uh, that bears a radius R1 and R3 separated by distance L. And then for our problem, we simplified this, you know, this physical picture, taking into the fact that this R1 now becomes equal to R3, and this L is nothing but the, sorry, so this L is nothing but the diameter. That's it. Okay. And your radius is of course diameter by 2. So we use that to indirectly, you know, find out the expression of F13, which was written in terms of S, where S was this number, you know, and this number for our case came out to be equal to 6, from which we calculate this F13, and then we calculated from the summation rule the F12, and from F12 we use the view factor reciprocity to basically calculate this F21. Okay. All right. So this is the problem that I asked you to solve it at your end. I hope you have done it. If not, please go through it and do it at your end. Uh, so this ends our you know, analysis of, you know, calculating view factors conveniently by using the summation rule and the view factor reciprocity relation, and, you know, augmenting the fact that some view factors which need to be obtained directly, you know, comes or you know, we can get it from the from the physical picture of the problem itself. For instance, we argued that this F11, in this case we argued that this F11 is equal to 0. That is typically because since this is a flat surface, there is no way that radiation can leave this surface and, you know, come and hit back onto this surface. Okay. So that's it for the third problem. And what we also did is, after, you know, having a brief, you know, analysis of this view factor, we looked into something which is known as radiation exchange in black bodies, and that we say that the effective radiation exchange can equivalently be represented as a radiation network, where the nodes now becomes the emissive powers, okay, and the resistances can, you know, be written like this. So, and we looked into two types of resistances. If it's a black body, we just have one resistance, which is nothing but the space resistance, that can be written in terms of the area and the view factor. If it's a real surface, instead of it being a black body, we have two kinds of resistance. The space resistance, of course, is always there. That is due to the orientation of the surfaces that they are. And the second is nothing but the surface resistance, which typically comes into the fact because the radiosity is not equal to the emissive power anymore for a real surface, and this in turn results, you know, in an extra resistance, which we call it as the surface resistance, written in terms of the emissive power, of course, epsilon. Okay, so this is the typical radiation network for a real surface, and we ended our discussion by writing what would be the net radiation exchange between two surfaces if they are real, okay, and written in terms of, you know, the resistances where the emissive powers were just the nodes. Okay, so for instance, it was just EBI minus EBJ divided by the resistances, and if we have two surfaces, we'll have two, you know, surface resistances owing to their emissivities plus one space resistance written in terms of its area and view factor. Okay, so this is something that we did in the last class. I'll stop here for a couple of minutes. And today, what we will do is we will extend this analysis of resistance network, extend this analysis of radiation using resistance network for something which is known as enclosures. So how do we draw? So the bottom line is that how do we draw the resistance network if we now have an enclosure? Okay, and before that we will I'll stop here. First of all, I'll stop here for a couple of minutes. If you have any doubts, you can ask. If not, we will go into the agendas. We'll go into the discussion, which will be centered around this agenda, that is the radiation network drawn for enclosures. Okay, but before that, going into drawing the radiation network for enclosures, we will have a brief exercise of drawing the radiation network for a couple of like simple cases, I would say. For instance, if I have a two infinitely long plates having properties this and this, what would be my radiation network? Okay, this is simple. We'll just have a brief exercise on it. And then let's say if I have a three zone enclosure, what would be my radiation network? And once that is done, we will solve a problem. It's a little bit involved problem. We'll solve it very systematically on, so basically we'll kind of solve a real, it's kind of a real life problem, uh, which we will use the concept of radiation, concept of, radiation network in enclosures to typically find out what will be the radiation exchange between surfaces in case of, in case of a more real life problem. Okay, so that's the agenda for this discussion. But before, going into the topics, I'll stop here for a couple of minutes. If you have any questions or suggestions, you can post it, or you can like discuss it, or else we'll begin in some time. Okay. Meanwhile, I'll just check if the recording is done or not. The recording is in progress. Okay. All right. Okay. If no questions, we will, start off with our first agenda today. That is, we'll try to draw radiation network for, couple of cases. So the first case, as you can see in your screen, is basically, two infinitely long parallel plates. The first plate, I call it as, let's say, number one. Let's say this plate is number one. The second plate is number two. Of course, the temperatures, the emissivities, and the areas of the first plate is given. Similarly, the temperature and the emissivities and the areas of the second plate is also given to you. What you need to do is you need to draw the radiation network for these, for this case, which, will start off like this. So as I say, for drawing the radiation network, so first of all, you need to identify that you have certain emissivities that is given, and let's not, let's first go into a generic case where my epsilon 1 and epsilon 2, they are not equal to 1, meaning that they are not black bodies, so they are basically real surfaces. Okay, which means that you will also have surface resistances coming into the picture. So these are real surfaces. So what we will do is what you need to do is you need to first start off from the emissive power node from one of the surfaces. And in this case, we will start off with, the surface 1, which we will represent it as EB1. And this EB1 is nothing but sigma times T1 raised to the power 4. Now, since surface 1, it's a real surface, meaning that it have emissivity is not equal to 1, which is less than 1, of course. I will have a space resistance, which will be 1 minus epsilon I by A1 epsilon 1. Okay, which is the surface resistance. So this resistance is the surface resistance for surface 1. Okay, now once you have written the surface resistance, there will be one resistance, that is associated with the space, and that is known as the space resistance. And we have seen that irrespective of, if you have a black body or a real surface, you will always encounter the space resistance, and that is associated with the orientation of the surfaces. Okay, so the space resistance can either be written as 1 by A1 F12, or you can write it as 1 by A2 F21, because you know that your A1 F12 is nothing but A2 F21 from the view factor reciprocity. So this is nothing but, so this resistance that we wrote here, so these resistances that we wrote here, you can write either of these two, either you can write 1 by F12, or you can write 1 by, 1 by A1 F12 or 1 by A2 F21, and these are known as the space resistances. And since after the space resistance, my second body is also a real surface, I will have one more resistance associated with the surface of, this second surface, and this would be nothing but 1 minus epsilon 2 by A2 epsilon 2, and this is your, surface resistance for 2, which is the second surface. And you need to close your node with EV2. Okay, but there is one simplification that we can do is, since these plates are infinitely long, you can appreciate that, and since these plates are flat, okay, I repeat, since these plates are infinitely long and these plates are flat, I can easily say that my F12, or my F21 is just going to be equal to 1. Why? Simply because, let's say if I consider plate 1, okay, and I apply the summation rule, I just apply the summation rule for plate 1, I can just write that F11 plus F12 is equal to 1. And simply you can write that F22 plus F21 is equal to 1. Either of the equations will do the job. Okay, and you know that this F11 is equal to 0. Why? Again, because of the physical nature of the problem, that these plates are infinitely long and they are flat, which means whatever radiation that leaves, either of this plate 1 or plate 2 should hit the other plate, which means, let's say I consider radiation leaving plate 1, it should hit plate 2. The entire of the radiation should hit plate 2. I hope you understand what I'm trying to say. Similarly, for this plate, since it's flat and it's infinitely long, I can say that my F21 is basically equal to 1. Okay, so I can just write that my F12 is just 1. Okay, and so is F21. So if you use F12 here, you need to find out this F12. If you use F21, you can also say that your F21 is basically equal to 1, which means that my net, so if I now write my net radiation exchange, that is Q12, and this is also equal to Q21, it just, you know, it can be minus of Q21. That depends on whether you are writing EB1 minus EB2 or EB2 minus EB1. That, it is the sign that basically need to be taken care of. But in magnitudes, Q12 will be equal to Q21 for this case. And this can be written as what? This can be written as EB1 minus EB2 divided by 1 minus epsilon 1 by A1 epsilon 1 plus 1 by A1 F12, and I know my F12 is just equal to 1, which means this is 1 by A1, because of the fact that my F12 is just 1, and then this would be 1 minus epsilon 2 by, this would be what? This would be just A2 times epsilon 2. All right. Okay, so this is your net. So this is just the expression for the net, radiation exchange between plates 1 and 2. Okay, if these plates are infinitely long and they are flat in nature. Okay, so this you can easily, argue from the resistance network, and you can see the power of this resistance network. So now you don't need to consider. So earlier what we did is we just consider one surface, evaluate the radiosity. Okay, then we consider the next surface, evaluate the evaluate the radiosity for that surface, and then using the, radiosities of these two surfaces, we then find out what will be the net radiation exchange. But the power of, using resistance network is that you just need to draw this resistance network, taking into account, of the fact that you need to consider the emissive power nodes, and these nodes now become the radiosity nodes J1 and J2. Why? Because for real surfaces, the only resistance that comes into the emissive power nodes and the radiosity node is nothing but is the space, sorry, is the surface resistance. So the moment I say that this becomes, so for instance, if I say that my surface 1 is a black surface, meaning that epsilon 1 is equal to 1, which means this resistance would turn out to be equal to 0, and I can just say that my J1 is equal to EB1, which means my radiosity is nothing but the emissive power. Okay. On the contrary, if I say that my epsilon 1 is less than 1, which means I have a real surface now, there will be a resistance between the radiosity node of surface 1 and the emissive power node of surface 1, and this resistance is nothing but the surface resistance. Okay. So, and of course, in between two radiosity nodes, okay, you will always have space resistances. This is also something that you need to, understand. Okay. All right. So this is the, this is the radiation network pertaining to this physical picture, where we had two infinitely long plates having areas A1 and A2, emissivities epsilon 1 and epsilon 2, temperature T1 and T2. Okay, I hope you have understood what we did here. Again, I'll stop here for a couple of minutes. If you have any doubts, uh, you can ask, of course. Okay. If not, we'll look into one more problem, which is nothing but, we call it as the tree zone enclosure. And again, the idea is to draw the resistance network. Okay. So that's what we will do. So again, before beginning, I'll stop here for a couple of minutes. If you want to have a look at this problem, or if you have any doubts associated with the previous problem, you can obviously, you know, speak and ask. Okay, if no doubts, now what we will do is we'll try to draw the radiation network associated with this figure, and this is typically known as a three zone enclosure, because we have kind of three plates that are, of course, that are you know kept in this manner. Okay. So again, the first task is, what we will do is, here in case of enclosures, your first task is to draw the radiosity nodes first. Okay. That is typically because since we have three surfaces, we will first draw the radiosity nodes and first, find out or evaluate what will be the space resistances. And then identifying the fact that whether my surface is a real surface or a black surface or a black body, we will draw, the emissive power nodes and the associated surface resistances associated in between the radiosity nodes and the emissive power nodes. Okay. So what we will do is we'll first draw the radiosity nodes for surface 1, 2, and 3. Okay. So let's say my radiosity node for surface 1 is let's say J1. My radiosity node for surface 2, let's say, is J2, and my radiosity node for surface 3, let's say, is J3. All right. So it's very easy to connect these radiosity nodes by the resistances. So have a look at the figure that between surface 1 and surface 2, that is between these and these surfaces, I will have a space resistance. Okay. And this space resistance is always in between, the radiosity nodes J1 and J2. And you can easily argue that the space resistance is nothing but 1 by A1 F1. Or you can write it as 1 by A2 F21. Either of this is fine as per the reciprocity relation. Okay. Similarly, I will have a space resistance. I will have a space resistance between 1 and 3. Okay. And this space resistance can now be written as 1 by A1 F13. Okay. And for the surfaces 2 and 3, so if you appreciate, we wrote one space resistance. We wrote one space resistance between these two surfaces. Then we wrote one space resistance between these two surfaces, and we'll just write one space resistance in between the third and the first surface. Sorry, the second surface. Which means my third, space resistance is something like this, which is nothing but, 1 by, you can either write it as A2 F23, or you can write it as 1 by A3 F32, whichever, whatever you wish to. All right. So this completes my space resistances, for in between the surfaces 1, 2, and 3. Typically, my space resistances, are in the form of a delta. That is typically because, I can have, a space resistance between this and this surface. I can have a space resistance between this and this surface. And I can have a simultaneous space resistance between this and this surface. And that's why it's kind of, in the form of a delta. Now, since these surfaces have emissivities and we consider the fact that epsilon 1, epsilon 2, and epsilon 3, the emissivities are less than 1, which means they are real surfaces, and this means I also now need to draw the associated surface resistances associated with these surfaces. So for surface 1, I can have my EB1 node, that is the emissive power node, and then I can have my surface resistance, and this surface resistance would now be equal to 1 minus epsilon 1 by A1 epsilon 1. And similarly, this exercise need to be done for the rest of the three surfaces. So for third surface, I can have a surface resistance like this, which is 1 minus epsilon 3 by A3 epsilon 3, and I can write, and I can extend the analogy for the second surface, which becomes, and of course this is EB3, this becomes equal to EB2, and this is 1 minus epsilon 2 by A2 epsilon 2. A2 epsilon 2. So that's it, guys. So this completes the radiation, the radiation network for a for a three-zone enclosure, where you have written the space resistances. So these are nothing but the space resistances, and these are your respective surface resistances, considering the fact that your surfaces are a non-black surface having certain emissivities, epsilon 1, epsilon 2, and epsilon 3 less than 1. Okay, I hope the pictorial representation of surface resistances, the pictorial resistance representation of radiation resistances are clear. How to basically start from, either you have to start from the radiosity node or you have to start from the emissive power node. If you are starting from the emissive power node, you a priori need to consider the fact that, indirectly you need to identify if it's a black body or it's a real surface. For instance, if I now say that, let's say my surface 1 is a black body, meaning that my epsilon 1 is just equal to 1, which means that this epsilon 1 is now 1, and I no longer have this surface resistance, meaning that my resistance network would just start from this node itself, and my J1 would now in turn be equal to EB1. That's it. Okay, and these are kinds of simplification that you need to do, as per the problem statement that you have in your at your disposal. All right, so I'll stop here. So this is one more, radiation network that we saw. So this the typical name of these kind of radiation networks are called three-zone enclosures. Radiation analysis of three-zone enclosures using radiation network, and and yeah. So similarly, you can also have a two-zone enclosure, or you can have a three-zone enclosure and things like that. And again, I'll stop here for a couple of minutes. If you have any questions associated with this, you can feel free to ask. Okay, if no questions, now what we will do is we will solve an important problem. I say it's important because it's kind of a real, life problem. Uh, or I would say it's a real world problem, precisely, which we will solve using, radiation network analysis. Okay, so I pose the problem here. So I think you can see it from your screen. Please go through the problem once. Okay, and I'll ask you to first go through this problem once, and then I will subsequently show you how to approach this problem and find a way. So there are multiple ways of approaching this problem, but we will try to solve this using by fitting a resistance network, I would say, for this case. and then we will see that how elegantly we can solve this problem by, using resistance analysis in this context. Okay, so this is the problem, and given that this F12, that is the fraction of radiation leaving surface 1, that is striking surface 2, where your surface 1 in this case is this heater, your surface 2 is this absorber plate. If you read this question, you will understand what is a heater and what is a absorber plate in this case. And it's given that the fraction of radiation leaving this heater and striking this absorber plate is equal to 0.39. Okay, that's given to you. So I'll stop here. I'll let you guys read this problem once, and then we will systematically approach the solution of this problem. All right. Let's quickly go through what this problem says. So it says that in manufacturing, the spatial coating on a curved solar absorber of area A2, which is basically this, its area is given to be equal to 15 meters square, which is nothing but the area of this solar absorber, is cured by exposing it to an infrared heater of width equal to 1 meter. So this heater width is given to be equal to 1 meter. That's given to you. The absorber and the heater are each of length L equal to 10 meter. That is the length of this absorber and the heater is given to be equal to 10 meter. Okay, and are separated by a distance h equal to 1 meter. Okay, so that's given to you. That is the distance of separation between this absorber and the heater is given to be equal to 1 meter. So by length, it means that if you extend this dimension into the other direction, okay, you can basically get the length here, which is given to be equal to 10 meter. And so is the case for the heater. Meaning that if I want to find out my area, that is my A1, it will just be equal. So I think my A1 is given. So A1 is just this width times the height. So it will just be equal to 10 meters square. That's it. Okay. Sorry. This A1 would be this width times the length. Pardon me for the mistake. So it will be just W times L, which will be equal to 10 meters square. That is your A1. And your A2 is given to be equal to 15 meters square. Okay, so that's the typical dimensions that we have. You just need to think of the fact that this absorber is extended in the third direction, and the length is essentially this length, which is 10 meters square, and so is the heater, which is extended in this direction. Of course, this length is also equal to 10 meter in this case. Okay, so given that, what they now say is that the upper surface of the absorber and the lower surface of the heater are insulated, meaning the only way heat transfer can take place is in these directions only. That is so heat cannot escape in these directions and in these directions, which means that these surfaces, so that's the upper surface of the absorber and the lower surface of the heater are insulated. Okay. What they now say is the heater is at a temperature T1 equal to 1000. That is T1 is given to be equal to 1000 Kelvin. Okay. And of course, the heater is not assumed as a black body, so it has an emissivity of 0.9, while the absorber is at a lower temperature, which is T2, which is 600 Kelvin, and it has an emissivity of epsilon 2, which is equal to 0.5. Okay, and most importantly, it says that the system is in a large room, that is this absorber heater system is surrounded, it's surrounded, so it is kept in a large room whose walls are at 300 Kelvin. For instance, you can say that the surrounding surface of this absorber and heater is a room whose temperature is 300 Kelvin. Okay, Having said that, you need to find out what is the net rate of heat transfer to the absorber surface. That's it. That's all you need to find out given this uh, physical scenario that you have. I repeat, you have an absorber of given emissivity and temperature, you have a heater of given emissivity and temperature, the corresponding areas are known. It is said that heat transfer can only take place inside this absorber heater configuration and not outside, because of the fact that the upper surface of the absorber and the lower surface of the heater, are insulated, and it is surrounded. This absorber heater, system is kept in a room whose, the temperature is 300 Kelvin. Given this context, and given the fact that my F12, that is the fraction of energy leaving, my heater, that is striking the absorber, is 0.39, that is already given in your problem, you are asked basically to find out the net rate of heat transfer to the absorber surface. Okay. Again, I'll stop here for some time. I want you guys to digest this problem, please, and then we will, try to solve this. So, having said that, we'll solve this problem using, radiation resistance analysis. There are multiple ways through which you can approach this problem, but one of these ways is the radiation network analysis that we will do here. But you can use any of your convenient, methodologies for having a go at this problem. Okay, so let's, kind of first start to solve this problem. So I'll begin. So we'll solve this problem very systematically. So what I will do is we'll begin by writing certain assumptions that we need to consider if we are to solve this problem using resistance analysis. So the first assumption is that I assume, so that's a common assumption. So I assume that there is steady state conditions everywhere. That is the first assumption. Second assumption is, of course, that I only consider radiation into my picture. So there is no convection heat transfer taking place. Okay. There is no convection effects. Okay. Third assumption is the fact that I I say this emissivity is epsilon 1, that is the emissivity of the heater, or the emissivity of the absorber is epsilon 2, which means that this is nothing but my hemispherical total emissivity, which means that my absorber and the heater surfaces are diffuse and gray. Okay, so my third assumption is that absorber and heater surface. So if you are solving this problem, at your end, you should start off. So always, start off a problem by writing in assumptions. And that's why, I'm doing that just to make things, systematic and convenient uh, for the solution. So the third assumption was that absorber and heater surfaces are diffuse and gray, meaning that my surface properties are not a function of wavelength, they are not a function of direction as well. Okay. And of course, there is one more assumption that you need to consider, that is, uniform irradiation and radiosity from all surfaces. And the fifth assumption is the most important assumption that will enable us to do to that will straight away simplify our analysis. That is, we will consider the surrounding room to be large enough and it behaves like a black body. Okay, so the surrounding room behaves like a black body. having said this, what now we can do is we can redraw the picture here, that there is an absorber, okay, and there is a heater. The absorber is termed as 2, the heater is termed as 1, and I can represent my surrounding as a third surface, you know, and this surrounding, which is a third surface, I'll call it 3. It have a temperature T3, which is equal to 300 Kelvin, and epsilon 3 is now just equal to 1. Meaning that my surrounding is large enough so that it can behave like a black body, and I can assume my surrounding as a third surface, which is nothing but a black body having emissivity 1. Of course, then the emissivities of my heater, which is my surface 1, is epsilon 1, that is given. Its temperature is T1. Similarly, I can write the same for my absorber surface, epsilon 2, and its temperature is T2. Of course, T1, T2, and epsilon 1, epsilon 2 are already given from here. Okay, I'll just write it down for the sake of completeness. My T1 is equal to 1000 Kelvin, if I'm not wrong. Okay, and epsilon 1 is equal to 0.9, of course, and this A1 is also given to be equal to 10 meters square, that is the heater area, and this T2 is given to be equal to 600 Kelvin, that is the temperature of the collector. Epsilon 2 is given to be equal to 0.5, and A2, that is the curved surface area of this collector, is given to be equal to 15 meters square. All right. So what in a way we did is we represented and reformulated our problem by assuming that my ambient is a black body into 3 surfaces: surface 2, surface 3, and surface 1. And what we will do is we can now map this surface as a 3-zone enclosure precisely, and we'll do the analysis of this 3-zone enclosure. We'll do the analysis in this 3-zone in this 3-zone enclosure. Okay, and then so the ultimate goal is to find out this this Q2, or you need to find out the radiosity of 2. Okay, once you know the radiosity of 2, you can get Q2 because of the fact that you know the surface resistances, which is 1 minus epsilon 2 by A2 epsilon 2. Okay, so that we will see how we'll do that, but you need to understand how did we map the system into a 3-zone enclosure kind of things, having 3 surfaces, 1, 2, and the surrounding surface, which is now mapped as a black body having a temperature T3 equal to 300 Kelvin, and emissivity, of course, is equal to 1. All right. So what I was trying to say is that, I'll just write it down. We can now view the system as a 3-zone enclosure, okay, with the third surface being being the surrounding as a black body. Okay, all right. So once we now we can so once we state that we can now view this as a 3-zone enclosure, let's try to draw the radiation network. That's what we can do, right? At least. Okay, so if I now try to draw the radiation network, remember what I said is for a 3-zone enclosure, always start off from the radiosity nodes. So I start off from the radiosity nodes of the first surface, which is J1. So my radiosity node for the second surface, let's say it would be J2, and the radiosity node for the third surface would be J3. And for connecting these radiosity nodes, as you guys know, there would be space resistances. For instance, the space resistance between J1 and J2 is nothing but 1 by A1 F1 2. The space resistance between 1 and 3 is nothing but 1 by A1 F1 3. And my space resistance between 2 and 3 is nothing but 1 by A2 F2 3. Now, since surface 1 and surface 2 are non-black bodies, I will have extra 2 resistances that will be the surface resistance corresponding to surface 1 and surface 2 in terms of their emissivities. So this would be what? This would be a 1 more resistance, and then it would be EB1, and it would be 1 minus epsilon 1 by A1 epsilon 1, and this would be what? This would be 1 minus epsilon 2 by A2 epsilon 2. You need to understand that I will not have, any extra resistances involved with surface tree, because typically my surface tree itself is a black body, which now means that I can simply write that my J3 is equal to EB3, which is nothing but sigma times of T3 raised to the power 4. Okay. So this completes the radiation, network for for this uh, for this for this physical picture. Okay, I'll stop here for some time. If you have any doubts, you can ask me. Again, you need to understand that keeping all these things in mind, what we need to do is we just need to calculate. Sorry, we just need to calculate this Q2. We just need to calculate this Q2. That is the prime, interest that we need to do. For calculating Q2, we'll first calculate this J2. And once you know J2, we will use the fact that, my Q2 will be just, EB2 minus J2 by 1 minus epsilon 2 by A2 epsilon 2. Okay. Typically, because I know the radiosity, then my, the net radiation exchange is just the difference between these two nodes divided by the resistance. That's it. Okay, so you need to remember that it is the prime variable of interest. And for calculating Q2, you need to first evaluate J2. And this J2, we will evaluate it from the resistance network. That's the algorithm. This you need to evaluate first. All right, guys. Having said that, I'll stop here for a couple of minutes. You can take your time, understand the resistance network, why we didn't, kind of added an extra resistance here, and all those things. You can reflect upon yourself, and then we'll start off with the remaining analysis. Okay. So now what we will do is we will basically use something which you guys all know actually, but we know it in some other context. We will similarly use that in this context as well. This is something which is known as Kirchhoff's, it's known as Kirchhoff junction law. In case of, if you studied class 12 physics, basically will be aware with all those things, Kirchhoff junction law, and all those things. Okay, what we'll use is we will exactly use this Kirchhoff junction law, Kirchhoff's junction law only. However, in this radiation context, in other words, what we will try to do is we will say that whatever the current that is coming in this direction, current meaning that now here it will be the flux. So in the very first class, I have said that if you want to draw resistances, your temperature become analogous to your voltage. Resistance is of course the resistance, and the current become analogous to the flux. So if I just do a continuity of flux at this junction, I can simply write that whatever the flux that will come from here to here will be, equally, or if not equally, at least it will be divided between this junction and this junction. Meaning that we'll just apply junction law at these, radiosity nodes. And we'll similarly apply this junction law at these radiosity nodes. That's it. That's the next step, of this analysis. So what we will do is we'll, apply junction law at, I call it as, let's say, radiosity node 1. All right. So if we apply, the junction law at radiosity node 1, you can say that the current that is coming in this circuit, that you can simply write it as what? You can just write it as the difference between voltages, EB1 minus voltage here now becomes the flux, my voltage now becomes the emissive power and the radiosity. Okay. So it just becomes EB1 minus J1 divided by the resistance, which is 1 minus epsilon 1 by A1 epsilon 1. And this is equal to what? This is equal to the difference between these two radiosities divided by these resistances. And so for this circuit as well, which I can write it as J1 minus what? J1 minus J3. But J3 is equal to EB3. So I'll just straightforward, write it as sigma times of T3 raised to the power 4 divided by 1 by A1 F13. And for the second circuit, basically for this, I can write it as, J1 minus J2 divided by 1 by A1 F12. All right. So this is my first equation when I apply the junction law at this radiosity node. Similarly, you can appreciate that in this equation, this J1 and J2 are unknown, out of which we need to calculate J2 first. That's what we said it here. Okay, which means and of course this EB1 and all these things are known because these are just properties. F13 we can find it out from the view factor analysis that we will see shortly. But the premier unknown is nothing but this J2 and J1, for which we require one more equation that we will get when we apply this junction law at the second radiosity node, that is at J2. What we will do is we'll now apply the junction law at J2. So if we do that, we can similarly write that my EB2 minus J2 divided by 1 minus epsilon 2 by A2 epsilon 2, and this is equal to the difference between these two radiosities divided by this resistance and these two radiosities divided by this resistance, which of course I can write it as J2 minus sigma times of T3 raised to the power 4 by 1 minus epsilon, sorry, not with this, it will be just the space resistance, it will be 1 minus A2 F23, okay, plus it will be J2 minus J1 by 1 by A2 F21. Okay, but A2 F21 from the law of reciprocity relation, you can write it as A1 F12, so we'll just write it as A1 F12 only. All right, so this is my second equation. Okay, this is my first equation, this is my second equation. I hope how we wrote this first equation and how we wrote the second equation, these things are clear. Okay, now try to have try to understand that apart from the unknowns which are J1s, which are J1s and J2s, these are the premier unknowns. For instance, this J, so these are the unknowns. I will just highlight it. These are the unknowns. Okay, these are basically the unknowns that we need to solve for, and that's why we have two equations. But unknowingly or knowingly, we also have some more unknowns which we need to basically find out. And these unknowns are nothing but the view factors. We don't know the view factors apart from just one view factor, which is F12, that is given in our case, which is equal to this. So this F12 is given to be equal to 0.39. Okay, but apart from this F12, we don't know. So we don't know this F13, that we don't know, and we also don't know this F23. So this view factor I will circle it with blue, because these things also we need to find out. So these things are also unknown. Okay, all we know is just this F12, which is equal to 0.39. Okay, now in order to solve these equations for J1 and J2, first we need to determine the unknown view factors and then substitute the unknown view factors here such that we have just two equations with two unknowns, that is J1 and J2. For that, we need to first, so the next step now is basically to evaluate F13 and F23. Okay, So let's first try to evaluate F13. What we can do is, so F13 is what? So F13 is fraction of radiation that is leaving surface 1, that is the heater, and that is striking, surface 3, which is nothing but the room basically, which is basically a black body. Okay, so what I can do is, let's start from where we know. So we have our summation rule in our disposal. So what I will do is, let's first apply the summation rule. So let's first apply the summation rule for the heater. Which is of course my 1. So using the summation rule, I can say that F11 plus F12 plus, F13, and this is equal to 1. That is from the summation rule. And I know that my F12, that is given to be equal to 0.39. Okay. This F12 that's given, that is given to be equal to 0.39, which means I know this F12. This is known to me. And from the physical picture of the heater, see, the heater is a flat surface, as you can see. The heater is a flat surface, which means under no circumstances, radiation that leaves the heater can strike back, to this heater itself. That is again because of the fact that, heat transfer can only take place in this direction only. And in under no circumstances, radiation that leaves this heater will strike back, to this heater itself. Yeah. For which, I can write that my F12 is basically equal to 0. Okay. That is because of the physical nature of the problem. And that's why I can now write, I can, evaluate one unknown at least, that is F13 as 1 minus of F12. And I know that my F12 is equal to 0.39, which means my F13 is 1 minus of 0.39. And this just becomes equal to 0.61. So I now know what is F13. At least I have figured out this view vector. Now, how to figure out the remaining view vector? How to figure out this F23? Because F23 is a little bit critical scenario, because this surface is a, this surface is a curved surface. It's not a flat surface. Had this been a flat surface, things would have been, much more simpler, I would say. Because see, what I need to find out, I need to find out F23, right? F23 is the fraction of energy that is leaving surface 2, that is striking surface 3, that is the room. Okay? But I could have easily written F23 is equal to F13 had this surface been a flat surface. And then due to symmetry, I can write that whatever the energy that will strike, the surface 3 from the heater, that fraction would be equally, that would be equal, that had this been a flat surface, and that it would basically strike this room, that is the surface 3. So that's the problem that we have. Okay. So the solution, what we'll do is, the solution is also, it's very interesting. What we will do is, we know that had this been a flat surface, we can easily say that my F23 is equal to F13. That is from symmetry. Because the area of this flat surface and this flat surface is exactly similar. And I know that the view factor is just a function of its orientation. Since the areas are same and since the orientation is same, it's kind of a symmetry argument that I can state that F23 is equal to F13. But we don't have that. So if we don't have that, let's make it like that. Okay. So what we will do is, we will assume a fictitious surface, or it's a mysterious surface that we will assume. Okay. I will say that the area of this surface is some A2 prime. Okay. And A2 prime is exactly equal to A1. That is from the symmetry and from the figure itself. And for this A2 and for this 2 prime, I'll name this surface as 2 prime. Okay. And from this 2 prime, and for this 2 prime object, or for this 2 prime surface, for the, what I can write it as, for the, you can just call it as an imaginative surface 2 prime, my A2 prime is exactly equal to my A1, which means from symmetry, I can easily argue now that my F, 2 F2 prime tree is exactly equal to F1 prime tree. Why? That is typically because my areas are same. My areas are same. So this is just symmetric, right? Which means whatever the fraction of radiation that will leave surface 1 that will hit surface 3 is exactly equal to the fraction of radiation that will leave this mysterious surface 2 prime and hit this surface 3. That is nothing but the rule. Okay? Which means I can just state that my F2 prime 3 is equal to F1 3 is already calculated, which is 0.61. So F2 prime 3 is 0.61. But this does not solve our problem, right? Because we just found out the view factor for this mysterious surface. But what is the view factor for the real surface? That is also that is something that we are actually interested in, right? So for that, that's a nature's way of helping us out. That is typically because see, for this mysterious surface, whatever the radiation that leaves the actual surface 2 that hits surface 3 passes through this mysterious surface. That is the line that you need to understand. The radiation that leaves surface 2 that hits surface 3 passes through this mysterious surface 2 prime, which means you know I can write. So the context is that since the radiation that leaves surface 2 heating surface 3, all of these passes through the the imaginative, I would say, the ima the imaginary surface. Actually, it's, sorry for my grammar, it should be an imaginary surface. I just wrote it wrong. Okay, so what I want to say is that since the radiation that leaves surface 2 heating surface 3, all of these passes to the imaginary surface, I can now write, I can now write that so what I can write that A2 F23 should be equal to A2 prime F2 prime 3. And from this, since I know my F2 prime and I know the corresponding area of the real surface and the imaginary surface, I can easily find out that this F23 is nothing but A2 prime by A2 times F2 prime 3. Okay, and thus this F23, see, A2 prime is what? A2 prime is 10. That is typically the heater area itself, and A2 is given to be equal to 15, I guess. Yeah, it's given to be equal to 15. And of course, my F2 prime 3 is equal to 0.61. 0.61, which means the fraction of energy now leaving the actual surface 2 that hits surface 3 is nothing but equal to, so if you do this math, it will just be equal to, it comes out to be around 0.41. Okay, that's it. That's the unknown F23 that we need to basically, that we were basically seeking for. So you can appreciate that just by considering, just by considering a fixed surface, it has, and calculating the view factor of that fixed surface, we have actually evaluated the view factor of the real surface, and that is the power of defining view factors. And again, that you can do, that is typically because view factor is just a function of configuration of surfaces. So symmetry assists us in a huge regard when you are calculating view factors. Okay, so that's it. We now know F23. We know what we know. We know F13 as well. This is F13. This means we now know all the view factors associated with the equations 1 and 2. Okay, so we know so this F12 now is known. F23 we have already calculated. Okay, and similarly F13 we already know, and so is F12 that has been already given to us. So if you just substitute all these view factors and substitute all the areas, I'll not do the math for the sake of repetitiveness, just substitute all the areas, substitute all the emissivities, and EB1 we all know this is nothing but sigma times of T1 raised to the power 4. Okay, and then take the value of sigma as 5.67 into 10 to the power minus 8. And if you just substitute all these things into equation 1 and 2, you will just have an equation involving two unknown J1 and J2. I will just write down the equations, what these equations would be. So the first equation, the first equation would just be, the first equation would simplify, to be minus 10 J1. This you can do it easily at your end. Just you need to substitute values and simplify it. That's it. It is minus 10 J1 times 0.39 J2, and this is equal to minus 510,582. This is my first equation, and my second equation simplifies to second equation basically simplifies to something like this: 0.6 J1 minus 1.67 J2, and this is equal to minus 7536. Okay, I name this equation as, let's say, what? Let's say this is 3 and this is 4. Okay, so that's it, guys. Two equations and two unknowns. That is easily solvable in however way you want to solve. So if you just solve this, what you will get is, so if you just solve for J2, you will just get J2 to be equal to 12487 watt per meter square. That's typically the radiosity for surface 2. But we are not done yet. Remember, we need to calculate the net radiation that strikes surface 2. And since surface 2 is not a black body, this means in between my radiosity node of surface 2, okay, which is J2, and there will be an EB2, and there will be one more resistance, which is 1 minus epsilon 2 by A2 epsilon 2. Which means the net radiation exchange with surface 2 Q can now be written as J2 minus, or since J2 is less, it's better to write EB2 minus J2 by 1 minus epsilon 2 by A2 epsilon 2. Okay, and if you just substitute all its values, because EB2 is sigma times of T2 raised to the power 4 minus J2 is already calculated, 12487. Okay, and this is 1 minus epsilon 2 is given to be equal to what? Epsilon 2, I think it's given to be equal to, let's see, epsilon 2 is 0.5. So, and A2 is also given to be equal to 15, I guess. Yeah. So, just 0.5 by, sorry. Yeah, it's 1 minus 0.5 by 15 times 0.5. And T2 is given to be equal to, I think T2 is equal to what? T2 is given to be equal to 600 Kelvin. So you just need to substitute this value of T2 as 600, and sigma is nothing but 5.67 into 10 to the power minus 8. Okay, so if you just do this math, just substitute this value and do this math, what you will get is, you will get Q, that is basically Q2, that is the net radiation exchange from surface 2, and you will get it to be around 77.1 kilowatt with the answer that I have. Now there is a minus sign, and that is obvious, typically because the surface 2 is at a lower temperature, which means net radiation is, so there is actually radiation that is not leaving surface 2. The net radiation is actually entering surface 2. That's the idea of this. That's the idea of this negative sign, which means the net heat transfer to, that is basically there is a net heat transfer to the absorber, and you can write that the net heat transfer to the absorber, that is basically the magnitude to be around 77.1 kilowatt. That's it, guys. That's the answer that we need to that the question is actually seeking for. Okay, so I understand this is a little bit of an involved problem, but it's a good problem, because what we did is we essentially reformulated a realistic physical problem into a zone, into a 3-zone enclosure. we did three, prime things here that you need to understand. First, we assume that the surrounding room, behaves like a black body, okay, and that the radiosity of the room is equal to its emissive power. That's the first thing. Second thing is that, and since we assume it as a black body, we could do the analysis using a three-zone enclosure that we just saw. Okay. The third thing, of course, is the view factors. Although some of the view factors could be, directly obtainable from the physical picture, the view factor, let's say f23, was difficult to find out just because it was a curved surface. Now, what we did is so if you guys very carefully see, since view factor is just a function of orientation, we considered a fixitious surface and then calculated the view factor f2 prime 3, which is the fraction of energy leaving this fixitious or imaginary surface 2, that is heating surface 3. And once we know that, since we know that whatever the energy that comes from the real surface should pass through this imaginary surface, this is very important. If this had not been the case, we could not have write this thing a2 f23 is equal to a2 prime f23 prime. This won't be possible if all the energy that is coming to the surface 2 did not pass through the surface 2 prime. But here, since it's not the case, since this fictitious surface is such that all the energy that comes from the surface 2 should pass through surface 2 prime, we could write that and indirectly find out the expression for f23, which is nothing but the actual view factor corresponding to the radiation leaving the actual surface 2, that is striking surface 3. Okay, and once that is done, we were basically required to solve two equations, this equation 1 and equation 2, and then find out the radiosity J2. Okay, and once this radiosity is known, you can use the fact that the net radiation exchange is this EV2 minus J2 divided by the space resistance, for which you will get the net radiation exchange with surface 2, which is Q2. That is the net radiation transfer to surface 2. And there's a negative sign, that is typically because there's a net radiation transfer to surface 2, and that's why we had a negative sign. Of course, its magnitude came out to be equal to 77.1 kilowatt. Okay, so this is the idea, and this is how we solve this problem. I'll again stop here for a couple of minutes. If you have any doubts, you can ask. Or else, this is the agenda that I had for today's discussion. Mainly we had solved problem involving resistance network in enclosures, and yeah. If you have anything to ask or if you have anything to basically discuss, I'll be happy to address. Okay. If not, then formally, as I said, this is the last session. It's a last formal session, but mostly, and as I said, we will have one more extra session in the so the agenda of the extra session is that I will touch upon some additional topics on radiation, and then we'll have a quick recap of the entire course. That is the the stuffs that we learned from week 1 to week 12. Okay, we'll have a quick recap of that, and that's it. We'll not keep the extra session too long. We'll end it to maybe 1 to 1.5 hours. That's the idea. But yeah, it's important that if you have any doubts in the extra session, please join, and that will be the last session for the course. Also, if you have any doubts related to the examination, patterns and all those things, it has already been addressed in the discussion forum. But yeah, if you have, primarily if you have any doubts associated to the assignment problems of all the weeks from 1 to 12, and also, on the discussion hours that we had, and on anything related to this course, please join the extra session. We will have the extra session mostly on 19th October. That is as per the plan. But yeah, you will be given. So once the extra session is confirmed, you will be given. You'll be notified. You'll be notified there, and you will also be notified through email, and also you'll be notified in the website. Okay. So that's the idea of the extra session. Hopefully, we'll meet for the last time once again on 19th October. But this was the last formal, I would say, uh, session that we had. Hopefully, the extra session will be there, and we will. So we are confirming it with the NPTEL office, and hopefully it will be there. Once the confirmation is conveyed from their end, it will be notified in the website, and it will be notified through emails as well. Okay. And of course, the agenda of the extra session I already discussed. If you have any doubts, feel free to join the extra session, where we'll basically be doing a quick recap of everything from the first week to the last. Okay, that's the idea. And yeah, so this is something that I seek to discuss today. If there are no questions, thank you all for joining this session. And yeah, if you and needless to say, if you have any doubts in between these weeks, and any doubts in the assignment, please join. Please post it in the discussion forum of the course, and any course member, be it a TA or anyone, will be happy to address your doubts. Okay. Thank you very much. Hopefully we'll meet next week on 19th October from 3 to 5. Okay. Thank you.